Hi everyone, I'm Jana and I spent my summer of HPC at EPCC in Edinburgh working with the fluctuating finite element analysis tool. FFEA is a code developed by the Computational Biophysics group at the University of Leeds. It is used to simulate large protein complexes at a scale that cannot be computed by traditional simulation techniques. While FFEA is without doubt a powerful tool, it has a fundamental weakness. It is slow. Despite already having an OMP parallelization, its performance currently limits it to small and fairly simple simulations. My project during this summer of HPC was to investigate the current parallel performance of FFEA, develop a strategy to improve it, and eventually start to implement an MPI parallelization. A goal that soon proved to be quite optimistic. But back to the current parallelization. It is implemented with OpenMP and offers two different parallelization strategies that can be selected using a flag in the makefile. These strategies are called within-blob parallelization and per-blob parallelization. Blobs are the proteins in the simulated environment and consist of protein segment nodes that can be divided into surface and interior nodes based on their position within the blob. The within-blob parallelization uses all available threads for each blob, distributing the nodes among them. The different blobs are still treated sequentially. Naturally, it produces the best results if there is only one complex blob. On the other hand, the per-blob parallelization bears the best results for multiple blobs, as each blob is only calculated by one thread, but multiple blobs can be handled simultaneously. I measured the performance using tests provided by the Computational Biophysics group in Leeds. Our initial test, two spheres with van der Waals interactions slowly colliding and drifting apart, proved to be far too simplistic for the parallelization to have any effect. After asking for a bigger, more realistic test, I received the Fabrin test, which was actually a bit too large in the beginning. After it still hadn't completed after 3 days of consecutive running, I started to adjust the input file to reduce the simulation time. While I did so, I also encountered the restart feature that made simulations with enabled van der Waals interactions quite challenging. For this test, the effect of the parallelization was clearly visible, but it was not exactly what we had expected when the team in Leeds told us that the current parallelization worked okay. OpenMP is limited to shared memory systems, but the current parallelization apparently didn't even scale well at this level. Setting up FFEA on Archer, the UK's national supercomputing service, was another challenge. Initially, I had planned to profile FFEA with Scalaska, but after many problems with Archer, I focused on gathering data about the parallel performance in different ways. For example, by comparing my runtimes of the Dynein test to those measured by the team in Leeds. The lack of data for the per-blob parallelization here was caused by a specific error called inverted element error that was investigated later on but turned out to be caused by random thermal fluctuation. However, more detailed profiling using either Scalaska or CrayPad is planned for the near future. I was also able to compile a hybrid MPI OMP version of FFEA, but due to the limited time frame of the project, I wasn't able to add some actual MPI functionality to it yet. This will be done in the future as the work on FFEA continues. The short-term goal will be an MPI parallelization modeled after the current per-blob parallelization strategy, as it requires little communication between processes. In the long term, a parallel computation of the van der Waals interactions will be necessary to achieve good parallel performance for realistic simulations. The work on FFEA just started. There's still a long way ahead.